Hi. In this video, we're going to begin our discussion of Unit 8, focusing on ideas of orthogonality and projection. At the end of this unit, you should be able to determine if two vector spaces are orthogonal to one another. You should be able to explain what is meant by the projection of a vector onto a subspace, and be able to compute the projection of a vector onto a subspace. You should be able to use such a projection to determine the error when we have an approximate solution to a linear system, and to be able to find the best approximate solution to an inconsistent system. Finally, you'll be able to find an orthonormal basis for any vector space using the Gram-Schmidt algorithm. In this video, we are going to introduce the idea of orthogonal vector spaces, and in subsequent videos, we'll introduce the ideas of the projection and the Gram-Schmidt algorithm. Let's begin with a discussion of what orthogonality means. We can start with a definition for what it means for two vectors to be orthogonal. Two vectors, u and v, are orthogonal to one another if and only if their dot product is 0. We can write the dot product as u dot v. We have seen before that this is perfectly equivalent to writing u transpose v when we presume that vectors are written as column vectors. So a row vector multiplied by a column vector will give us a scalar. This definition of orthogonality of two vectors matches perfectly well onto the geometric concept of orthogonality. If we think about the cosine law, this is a review of material that we saw in Unit 2. The cosine law that relates the angle between two sides of a triangle, A and B, to the length of the opposite side, C, can be interpreted in the language of vectors and rearranged to give an expression for the cosine of the angle as the ratio of the dot product of two vectors over their lengths. This relationship between the angle and the dot product directly leads to a requirement that two non-zero vectors can be orthogonal to one another if and only if they are at right angles to each other. That is, the angle between them is pi over 2 radians, or 90 degrees. And this maps perfectly well onto the definition of orthogonality with a dot product of 0, because u dot v equals 0 means that we have 0 over something, which is of course 0. If cosine of an angle is 0, the angle must be pi over 2. So we have a consistent definition. Why do we use this dot product definition of orthogonality instead of the angle? Well, the main reason, or one of the main reasons, is to allow a definition that includes the 0 vector. With the 0 vector, we can't define an angle that makes with something because it's a point. In this angle-based definition, if one of the lengths is 0, we have something over 0 giving us an undefined answer. If we purely focus on a definition of orthogonality involving the dot product, however, we get the result that the 0 vector is orthogonal to every vector, including itself, because u dot 0 is, of course, 0 for any vector u. Okay, So we have a definition for orthogonality between two vectors that is entirely consistent with our definition, our geometric intuition of what orthogonality might mean, but is also generalizable to the zero vector. That's for orthogonality of two vectors. Now let's define orthogonality of two vector spaces, two collections of vectors. Two vector spaces, U and V, are defined to be orthogonal to one another if and only if the dot product of every vector from U with every vector from V is 0. In other words, every vector from U has to be orthogonal to every vector in V. We might write this in mathematical notation. U is orthogonal to V. This kind of upside down T is the notation that we read as is orthogonal to. U is orthogonal to V is perfectly equivalent to saying that U transpose V, or the dot product of U with V, is 0 for every possible U in the vector space U and every possible vector V in the vector space V. That is a definition. It's not a very satisfying one to find out if two vector spaces are orthogonal to one another, because we can't evaluate the orthogonality of every single vector in a vector space, as there's an infinite number of those. Luckily, we can write an equivalent statement. Two vector spaces U and V are orthogonal to one another if and only if every vector from a basis of U is orthogonal to every vector from a basis of V. Essentially, we do not need to look at every possible vector in U and every possible vector in V. It suffices for us to look at every vector in a basis for U and every vector in a basis for V. So if we have some set of vectors that together span U, their linear span is U, they are a spanning set of U, or a basis, and T is some set of vectors Ti, which together span the vector space V. U is orthogonal to V, is equivalent to every vector from S dotted with every vector from U, from T, giving 0. Why is this true? Why is this enough? Well, we can see that as represented here. If U is some vector from vector space U, and V is some vector from vector space V, then U can be written as a linear combination of the vectors from S. And V can be written as a linear combination of the vectors from T. If we think about what this product of two linear combinations look like, well, it's a sum of terms that all have the general form of whatever the constant was for, say, S1, whatever the constant was for T1, plus the dot product of S1 and T1. Then plus the appropriate coefficients for S1 and T2 times their dot product. And we would do this using S1 and every possible T. Then we'd move on using S2. Sorry, there's a little typo here. S2, the appropriate coefficients for S2 and T1 multiplied by their dot product, the appropriate coefficients multiplied by the dot product, and so on. Every term in this sum is a dot product of a vector from S and a vector from T, and the product of some coefficients. The only way that this is going to be 0 for every possible u and v, that is for every possible combination of coefficients a and coefficients b, the only way we're going to get that is if all of these dot products are 0. Right? And if the dot products are 0, then it doesn't matter what these coefficients are. This dot product will always be 0. So this actually gives us now a tool that we can use to evaluate the orthogonality of two vector spaces. If we have a basis for one and a basis for another, we can simply evaluate the dot product of each basis vector against each other basis vector and show that they are 0 or not. If they are not, if the basis vectors are not all 0 when we take their dot product, then the vector spaces are not orthogonal. Those were a mathematical definition. Definition using ideas of the dot product. It often helps to have a visualization, to have some intuition for what it means for two orthogonal vector spaces. Let's take a couple of examples to try to see what we mean by here. First, let's consider a case in 2 dimensions, although the same idea sort of extends to 3 dimensions. 2 lines passing through the origin are, of course, vector spaces in 2 dimensions, subspaces of 2 dimensions. 2 lines that cross at a right angle from one another are a pair of orthogonal vector spaces, as we show here. This also gives us a little bit of an intuition for why we only need to check the orthogonality of a basis. If this vector u that lies on the line u can be considered a basis for this vector space, and this other vector v that lies on the line v can be considered a basis for the vector space v, and we see that when these 2 vectors are orthogonal to one another, the lines that pass through that sort of extend from these vectors are orthogonal to one another. This is one example, but a fairly trivial one because we're just dealing with lines in 2 dimensions. Let's move up to a 3-dimensional case. Another example of orthogonal vector spaces is a line that intersects a plane at right angles, at the origin, of course. So a line passing through the origin is a vector space, a subspace of R3. A plane passing through the origin is also a vector space in 3D. And what do we mean by a line that intersects a plane at right angles? We mean a line such that we can draw any line on the plane, and any line that sits on the plane will be at a right angle to that plane. Shown here are 2 examples, a vector on the plane, a vector on the plane lying at right angles to this line. This also kind of demonstrates the idea of looking only at a basis. Any vector that sits on this line is, of course, a basis for this line. So we might imagine this vector here as being a basis for that line. The vector here that sits on a plane, the vector here that sits on the plane are 2 vectors from the plane, but they are clearly linearly independent. They are not scalar multiples of each other. And thus, these 2 vectors form a basis for the plane. one of these is orthogonal, the other is orthogonal. And the fact that these two are orthogonal to one another will lead to every possible linear combination of these basis vectors also being orthogonal. Okay, so that's what we mean by orthogonality of a vector space. Quite simply, there are two vector spaces where every vector from one is orthogonal to every vector from another. Now that we have this idea of orthogonality, we can introduce a very interesting and very important concept. That is that the row space is orthogonal to the null space. Why is this? Well, let's let U here be the null space of a matrix. So we're saying U is null space A. What does this mean? This means that A times U has to equal 0 for every U. U are the set of solutions to this homogeneous system. Let our vector space V be the row space of A. Now, the row space of A is the column space of A transpose. If V is the column space of A transpose, then A transpose times X equals V must have a solution. Why? Because the column space of a matrix means the set of right-hand sides that have a solution. There must be some X such that this is true. We can write this in more mathematical notation. If V is the row space, then V is the column space of A transpose. And for every V, there exists some X where V is equal to A transpose X. Now, these two results lead to V transpose necessarily being 0. Why is this? V transpose U, well, we can substitute V transpose if V is A transpose X. Substitute this, A transpose X transpose. We propagate a transpose in by reversing the order and applying the transpose to each piece. So we have X transpose times A transpose transpose, which gives us back A. X transpose A times U, which is X transpose AU, but we know that AU has to be 0, so X transpose 0 is, of course, 0. Every vector V from the row space and every vector U from the null space has a dot product of 0. The two vector spaces are orthogonal to one another. This adds a relationship to the already fairly deep relationship that we had seen before between the row space and the null split space. Previously, we saw that the row space and the null space share the same parent space. That is, if A is an M by N matrix, both the row space and the null space are subspaces of Rn. They have the number of columns of A. And we saw how the dimensions of the row and the null spaces sum up to the dimension of the parent space. The dimension of the row space plus the dimension of the null space is the dimension of Rn. The first of these, the dimension of the row space, is the rank. The dimension of the null space is the nullity. The rank of A plus the nullity of A equals the number of columns of A. We have now also added in this extra piece that the row space and the null space are orthogonal. 3 relationships between the row space and the null space. This sort of relationship has a special definition, the concept of an orthogonal complement. We say that two vector spaces are orthogonal complements to each other if, first of all, they are orthogonal, and that together they span the entire parent space. We discussed before in the last unit how when we take the direct sum of two vector spaces, this is saying we take all of the possible linear combinations from one vector space and another vector space. If that direct sum generates the whole vector space, and the two vector spaces are orthogonal, we say that they are orthogonal complements. And we use this notation here. Again, we're using this orthogonal symbol, but we're now using it as a superscript. V equals U superscript. Orthogonality means that V is the orthogonal complement of U. And it's a reciprocal relationship. If V is the orthogonal complement of U, then U is the orthogonal complement of V. In the two examples we just looked at, let me go back and take a look at these. Both of these vector spaces, pairs of vector spaces, were in fact orthogonal complements. We had two lines in 2 dimensions. Two linearly independent vectors in 2D spans the entire space, and these vector spaces are orthogonal. In this case, a line and a plane. We have a basis for our line, 2 basis vectors for our plane. This gives 3 linearly independent vectors in in R3. They must span R3, and the 2 vector spaces are orthogonal to one another. They are orthogonal complements. If I had had 2 lines in 3 dimensions, 2 lines in 3 dimensions might cross at right angles. They might still be orthogonal, but 2 lines are not sufficient to generate 3-dimensional space. So 2 lines in 3 dimensions would not constitute an orthogonal complement. We need to be orthogonal, and the vector spaces have to be big enough that they generate the whole space. Okay. So this gives us a result here that the row space is the orthogonal complement of the null space, and of course the null space is the orthogonal complement of the row space. This directly extends to a relationship between the column space and the left null space because, of course, the column space of A is simply the row space of A transpose. And since we've just seen that the row space of a matrix is the orthogonal complement of the null space of that matrix, the row space of A transpose must be the orthogonal complement of the null space of A transpose. The column space of A is the orthogonal complement of the left null space of A. The left null space of A is the orthogonal complement of the column space of A. This relationship means that the same 3 rules apply. The column space and the left null space share the same parent space. The column space and the left null space are subspaces of Rm, where m is the number of rows of A. This is a relationship we've seen before. The dimensions of the column space here, the dimensions of the column space and left null space sum to that of the parent space, Rm. and the column space and the left null space must be orthogonal to one another. These two pairs of relationships, the row space and the null space, the row space and the null space are orthogonal complements, and the column space and the left null space are orthogonal complements. Can be added into this now picture of how a matrix can be divided into these sort of four fundamental subspaces. When we start with a matrix A that has m rows and n columns, we can first of all think about a piece of this that describes Rn, and another piece that describes Rm. On the Rn side, we have the row space and the null space. Their direct sum is Rn. That is, if we take all linear combinations of them, we generate the original space. They are orthogonal to one another. Every vector in the row space is orthogonal to every vector in the null space. We can say that they are orthogonal complements. Very similarly, on the Rm side, we have a column space and a left null space. Their direct sum generates the whole space. They are orthogonal to one another. We say they are orthogonal complements. Okay. That wraps up our introduction to the idea of orthogonality. We've discussed what orthogonality between two vectors means, what orthogonality between two vector spaces means, and we've seen how there's this deep relationship between the row space and the null space, the column space and the left null space as orthogonal complements. In the next video, we are going to move on to extending these ideas of orthogonality into ideas of projections and how this relates to least squares solutions to problems. Thank you, and goodbye.